So far, we've used accuracy to validate models. Let's see why this isn't always a great idea. Welcome to this video on classification. My name is Kevin Fiesel. I'm the proprietor of Galaxy Services LLC, a consulting firm which specializes in work all across the data platform space, especially SQL Server. So far in this series, we have used one measure for testing the quality of models that we have trained: accuracy. Accuracy is a very useful measure, but it's not the only one, and there are some cases in which accuracy can be very misleading. Let's head to the classroom and talk about this topic. I'm going to use a canonical example of why accuracy is not enough to determine a classification model's quality. Let's suppose that there is some sort of rare disease out there and it affects 1 in 10,000 people. The treatment is a rinse of orange juice and toothpaste every day for a week, which is already making me a little nauseous, I will admit. But if people don't take that, well, 3 weeks from today, they get Thanos snapped out of here. Good news! I can train a model that is 99.99% accurate when it comes to discerning if a person has the disease. I'm ready for my Nobel Prize. That's right. No ifs, no elses, no trees or calculations. Just tell the person they're fine and send them right along their way. And you know what? It'll be right for 9,999 out of every 10,000 people you see. But this is actually a terrible model because it misses every single person with the disease. In this case, we have two problems. First, we have extreme class imbalance. For every one case with the disease, we have 9,999 people without it. That one person ends up getting lost in the numbers. The second problem is extremity. If you rinse with orange juice and toothpaste, that's nasty, but you will eventually get over it. If you get Thanos snapped away, it's kind of hard to get over that. Therefore, it would be better for us to err on the side of telling people to drink the swill rather than telling people who will disappear that everything will be fine. This leads me to the confusion matrix, a matrix that compares reference results versus predictions for classification scenarios. By the way, when I say reference here, I mean the actual values that we see from labels. Also, I'm going to show you some examples from R because I like the way that they display confusion matrices. When we get to the demo, we'll see how things look in Python. In addition, I'm also going to show you a simple multi-class confusion matrix based on the iris dataset. We are still going to focus on two-class classification right now, but all of the terms we'll use actually work for multi-class classification as well, and this is a case where I think it's better to start with a visual understanding of the more complicated scenario so that we can understand how the two-class scenario simplifies things. There are a few things we can immediately see here. First, there are 3 classes of iris. Yes, I'm using the iris example. Get over it. We have Setosa, Versicolor, and Virginica. This is an example of me training on some set of the data and then testing with 30 total samples, of which 6 were Setosa, 12 Versicolor, and 12 Virginica. Our first calculation is accuracy, which I'll define here as the sum of true positives and true negatives divided by the number of predictions. In visual terms, the blue boxes are our numerator, and the red boxes are what we would add to the blue boxes to get to the denominator. In other words, we got 6 Setosa classifications, 11 Versicolor classifications, and 11 Virginica classifications correct. We miscategorized one iris as Versicolor when it should have been Virginica, and one that should have been Versicolor, but we called it Virginica. This leads to a total of 28 out of 30, or an accuracy of 93.3%. In a normal set of circumstances, accuracy is a pretty good baseline measure, assuming you do not have a strong class imbalance and don't strongly care about one class versus another. The next that we're going to look at is positive predictive value, which is something that we do per class. The numerator is the sum of the times we predicted a specific outcome and that outcome actually happened, or in other words, the sum of predicted values of versicolor given a reference value of versicolor. Then we divide it by the total number of versicolor predictions. Our positive predictive value for versicolor is 11 out of 12, or 91.7%. By contrast, the positive predictive value for setosa is 100%, because every time we predicted setosa, we got that one right. Negative predictive value is the flip side of positive predictive value. The idea here is, assuming we did not predict versicolor, how often were we right in not choosing versicolor? There are a total of 18 non-versicolor predictions, so we take the sum of cases when the result was not versicolor, and we divide it by the total number of non-versicolor predictions. That's 17 out of 18, or 94.4%. One important thing to remember about negative predictive value in a multi-class scenario is that our prediction doesn't need to be completely correct. It just needs not to be the class that we care about. For example, let's suppose that these 6 setosa predictions were actually all for Virginica irises. Our negative predictive value would not change because we did not predict versicolor and the result was not versicolor. This can be a little tricky to wrap your head around sometimes, but there are cases when negative predictive value can be quite useful. The next formula is sensitivity. This asks the question, if an event actually happens, how often do we predict it? Or in other words, if the actual iris is of type versicolor, how often did we predict that it would be versicolor? This question, like positive and negative predictive value, is on a per class basis, so the sensitivity for versicolor is 11 out of 12, but for setosa it is 6 out of 6. Specificity is to sensitivity what negative predictive value is to positive predictive value. Specificity looks at all of the times an event did not happen, or the actual class was not our class of choice. In that case, how often did we predict something other than that class? In this case, you can see where we look at all the instances where the reference value differs from versicolor. So there are 18 examples. Of those 18 examples, we predicted something other than versicolor for 17 of them, and we predicted versicolor once. Thus, our specificity for versicolor is 17 out of 18. And this discussion of sensitivity and specificity really ties in with our imbalanced data problem. Thinking back to the toothpaste and orange juice example, a specific test would do a good job of rejecting people who do not have the health condition. By contrast, a sensitive test would do a good job of detecting people who do have the health condition. The problem in our fallen world is that there is an explicit trade-off between specificity and sensitivity, meaning that the better we do on one, the worse we're going to do on the other. It is really hard to improve both of them at once. Typically, in order to do that, we need to find a better algorithm, train the model a different way, or gather more or better data. But if we keep fixed the choice of algorithm, hyperparameters, and training data, we can choose to emphasize sensitivity to capture as many of the disappearingly ill as we can. The downside is, by focusing on sensitivity, we reduce the specificity. We are no longer as confident in telling people, you don't really have the disease, and we will end up subjecting some group of people to orange juice and toothpaste when they otherwise would have been fine. That's a lot of charts and formulas to throw your way, so let's take a look at our heart attack data set and see how all of these pieces fit together. The notebook for this demo will be a little different from our first set of notebooks. Here, I'm going to compare the 4 algorithms we've talked about so far: CART, Random Forest, XGBoost, and Light GBM. We'll see how they do against this heart attack data, not just in terms of accuracy, but also the other measures we've discussed. We'll import the standard set of libraries, as well as the tree and ensemble models for scikit-learn, and then XGBoost and Light GBM. We'll create 4 classifiers in total, so I'll keep them distinct by adding an underscore and then the type of the classifier at the end. So we have CLF underscore cart for a cart classifier, CLF underscore RF for a random forest classifier, and so on. I am also going to set a fixed random seed so that I get a consistent outcome each time. That will make it easier so that I can give you exact numbers and you can get the same outcome if you try it yourself. Our dataset is the same heart attack dataset we've looked at a few times, so I won't bother reprinting the measures. Instead, let's just get our test and training datasets in place. Then, in this cell, we're going to train each of the 4 algorithms, building 4 separate trained models off of the same training data. After training each one, we'll generate predictions for the test dataset. Now let's take a quick peek at those accuracy scores. We can see that random forest, XGBoost, and light GBM are all in the same neighborhood. In this case, XGBoost is a little lower than the rest of them, but some of this is just luck of the random state draw. CART will sometimes get as high as 82%, but usually it stays in the 75% range, as we see here. So CART is a little worse, and the rest are in a fairly tight range. Now let's look at the confusion matrix. I'll focus on the matrix for CART right now, and I can get the confusion matrix by importing it from sklearn.metrics. What we have is honestly kind of ugly compared to the nice looking confusion matrix in R, but at least it does display results in a readable fashion. However, I need to point out that the column and row orders are different from what we have in R. In R, columns represent actual values, rows represent predicted values. Here, the rows represent actual values, the columns represent predicted values, so it is flipped. In other words, there were 30 cases where we had no heart disease and we predicted no heart disease. Those are good outcomes for us, and in a 2-class problem like this, we typically call those true negatives. Now, you might say, hey, not having heart disease sounds like a good outcome, not a bad one, so why are we calling that the negative outcome? And I agree, not having heart disease is a good thing. But when I talk about negative and positive here, I don't mean this in some normative sense. Instead, we are asking the question, did the event happen? If the event did happen, that's a positive. If it did not happen, that's a negative. The event itself could be a good thing, or it could be a bad thing, but we are not judging the normative value of the event. Instead, we are assuming the negative outcome is the default, and something happens that causes us to flip the state, which becomes the positive outcome. Moving on, there were 17 cases where we predicted there would be heart disease, but there wasn't. In other words, we have a false positive outcome. Looking at the first row, that says we had 47 people without heart disease, and we got 30 of those predictions right. Next, there were 38 cases where we predicted heart disease, and the person did in fact have heart disease. These are called true positive outcomes. Finally, we had 6 cases in which the person did have heart disease, and we predicted they would not. Those are called false negatives in our 2-class world. With that matrix in mind, let's now print out the classification report for CART. These results look quite a bit different from what we saw in R, so let me explain what's going on here and how all the pieces actually do fit together. We get 2 measures back for each class, precision and recall. The precision score asks the question, if we predict a particular outcome, what is the likelihood that this is the outcome? In Python, we calculate this along the vertical axis. For class 0, meaning no heart disease, we were right 30 times and wrong 6 times, for a precision of 83%. For the heart disease class, we were right 38 times and wrong 17 times, so our precision for predicting heart disease is 69%. Recall, meanwhile, asks, given a particular outcome, how likely were we to have predicted this? In Python, we calculate this along the horizontal axis. For class 0, we predicted 30 people would not have heart disease, and we're correct about it. But we also predicted 17 people to have heart disease who turned out not to have it. So our recall is 30 divided by 47, or 64%. For the yes heart disease scenario, we were right 38 out of 44 times, for a recall of 86%. Basically, we were very good at catching the people who had heart disease, but this came at the cost of misdiagnosing a larger number of people who did not have the heart disease. The third measure on here is called F1 score, and this is a combination of precision and recall. The purpose of this score is to give us a more holistic view of our results in one measure. Our F1 score for CART is 0.74 to 0.75. In fact, you can see that all of these scores seem pretty close to our accuracy, and that's close to the ideal outcome, because what it means is we have a balanced data set and no bias toward finding people with heart disease or people without heart disease. Now let's quickly look at the other 3 algorithms. I'll start with random forest. We can see that random forest is better across the board. We have 1 fewer false negative than CART and 8 fewer false positives. That's why our precision and recall scores are all in the 80+% range. For XGBoost, we were just as good at not providing false positives, but we did have a couple more false negatives than CART. This is the primary reason our scores are a little bit below random forest. Finally, LightGBM. This was just as good at random forest in minimizing false negatives, but we had 1 extra false positive report. Basically, all 3 of these ensemble algorithms did well, and we're all on the same path. But now let's switch things up a bit. The heart attack dataset, as I mentioned, is a very balanced dataset. There are almost as many people who had heart disease as people who did not. But let's look at a slightly different scenario. I've taken out all but 24 of the heart disease cases, while leaving in approximately 150 cases without heart disease. Let's see how each algorithm performs. We can see that CART's accuracy is approximately 77%, and the other 3 techniques are in the 87 to 89% range. But let's dig in a little deeper. Once again, I'll start with CART's confusion matrix and classification report. CART ended up getting 35 cases of people who did not have heart disease correct, providing false positive reports on 6. Meanwhile, it struggled on the cases with heart disease, getting only 3 out of 8 correct. That leads to a poor precision and poor recall for heart disease cases, and it shows that CART, to an extent, minimized the heart disease case because of a lack of balance. In short, not great, especially because we're a bit more interested in predicting the cases where a person did end up with heart disease. So now let's take a look at random forest. Random forest was outstanding in cases where the person did not have heart disease, but it was only 50-50 on cases with heart disease, again failing us somewhat. Also, I'd like to take a moment and tie back 2 measures that we talked about in the classroom but haven't seen here so far: specificity and sensitivity. As a quick reminder, specificity asks the question, if an event's outcome is negative, how often do we predict a negative outcome? Well, it turns out that for this 2-class problem, specificity is the same thing as recall on the negative case. There were 41 people who did not have heart disease, and we got 40 of those correct for a negative class recall, or a specificity, of 98%. Meanwhile, sensitivity is asking the question, if an event's outcome is positive, how often do we predict a positive outcome? That's the same thing as recall on the positive class. I had 8 cases of heart disease in the test data, and I was right 50% of the time, meaning my sensitivity is 50%. We would say that this random forest model is a specific test, but not a sensitive test, based on the data that we have available to us. In other words, it does a great job of saying who does not have the heart disease, but not a great job of saying who does have heart disease. Okay, now that I've tied sensitivity and specificity back to recall in this two-class scenario, let's look at XGBoost and see how it fares. It was a little worse at predicting a case without heart disease, getting only 38 out of 41 correct. But it was also a little better at predicting heart disease, getting 5 out of 8 right. Therefore, this test is a bit more sensitive and a little bit less specific. That is, assuming there is a meaningful difference between getting 4 out of 8 cases right and 5 out of 8 cases right, we could make the claim. But that's a discussion for another day. If we suppose that there is a reasonable difference here, and that this would be stable with a larger amount of data, those are big assumptions, I know, but stick with me here. Well, then we might actually prefer XGBoost to random forest in a medical scenario, even though random forest is a little more accurate for this data. That's because the cost of a false negative is considerably worse in this case than a false positive, as false negatives may mean that people go untreated, whereas false positives may mean that people get unnecessary treatment. Let's wrap things up by looking at light GBM. Running the final pair of cells, we can see that the confusion matrix for light GBM is exactly the same as XGBoost in this scenario, so the two models would be interchangeable for our uses. And now you know why accuracy is not the entire picture. There are plenty of other measures of model quality for classification, and we can derive most of them from the confusion matrix. In the next video, we are going to shift away from tree-based algorithms altogether and begin looking at some of the non-tree algorithms for classification. Our first algorithm will be k-nearest neighbors. We'll have links and show notes in the description below, and until we see each other in the next video, take care.